This is probably the size of Lonar.
Okay. So how's the wildfire situation around you now?
Oh, thank you for asking. California is in the middle of a gigafire, which is when over 1 million acres have burned. And it's mostly up further north in San Francisco,
okay,
up by the coast. And we are getting smoke here. So the air quality is shifting with the wind.
Okay.
But most of the other fires that were burning in August and September are now contained.
Okay, so that's good.
But it's still, it's disheartening. It's one way to lose the water.
Yeah. So I saw a couple of your posts on Facebook about that. So then I got it that you are pretty close by somewhere.
Yes, we were probably within a half a mile of the zone for about a week. There was a zone of evacuation warning.
Okay.
And we were not worried because we were within the city limits.
Okay.
But I have a horse, and he was very close.
Okay.
A few minutes walk to the zone, and I have friends who had to evacuate their animals.
Okay.
But it was but I also have friends who lost their houses to the fire.
Oh.
So can you imagine having 20 minutes to leave and then take everything that you can and not know whether you'd come back? So that was
Yeah. And that too in such a difficult situation of COVID.
I know. It's just this is a really crazy year, isn't it?
Yeah.
So guess we all have a lot to be grateful for, and that's when you have to focus on that.
Yeah.
So I think Lonar crater being here, I mean, has got some resemblance with the crater on this. I mean, are there any kind of correlations?
Chinta, you're studying Lonar crater in your spare time. So actually, I put a picture of Lonar in this slide deck further down, just to remind people. I mean, India. So Siddharth Pandey is in the middle of teaching an online astrobiology course, and I'm one of the instructors. But we have, I think, 800 people who signed up, and from all over the world. It's pretty exciting. But one of the projects that the class is doing is looking for analog sites within India. And there's so many wonderful planetary analog sites. And we're hoping to help, make a compilation or start a compilation that everybody can contribute to. Cool. And there are so many places I would like to visit within India. Oh, and I'd like to go on a camel ride. But anyway.
No, I think we should definitely organize a field visit to Lonar.
I think that would be wonderful. I mean, we were hoping to go again this year, and obviously certain things got in the way, but I will come back when it's possible. And I think Sean will come with us, and Sean Wright, and who's been to Lonar many times, and a few of the other adjunct faculty at Amity. And we'd love to make a bigger expedition. When I went, we went by train one way and flew back the other way. So it was good experience.
So Vaibhav, shall we start in like 2 minutes or so? Or Vaibhav, are you there?
Yeah, I am here. So we have live on YouTube now, and around more than 50 participants are there. So we can start in minute or so.
Okay.
Are we waiting for the are we waiting for the YouTube people? Or waiting for the YouTube channel?
There are not YouTube. We can have some more participants here. Maybe yeah. Okay, I think
Should start, right?
we can start. Yeah.
Yeah.
Okay, great.
Uh, Good evening, everyone. I'm Chintamani Pai. I welcome you behalf of Space Geeks Mumbai, and good morning to Dr. Jen Blank, who is joining us for World Space Week celebration all the way from USA. And as you know, that she has been expert working on different aspects of Mars, and she's associated with NASA Ames Research Center and Blue Marble Space Institute of Science. Ma'am, it's great pleasure having you here, and we all are excited to listen to your talk. And let me briefly explain about Space Geeks Mumbai before we start with your talk. So Space Geeks Mumbai is a young startup working in the field of space education, space science, and space technology, co-founded by myself, Chintamani Pai. We have then Dr. Virendra Yadav and Dr. Ankush Bhaskar, and we also have experts associated with Space Geeks here, Dr. Vaibhav Raut, Vishnu Verma, and Hari Tejas Iyer. So the whole aspect behind starting Space Geeks was to create a talent pool where we can not only just do space outreach, but also do some research activity, some space technology aspects. And with that motivation, we started Space Geeks, and we even in during pandemic situation we are continuing our activities. And uh, World Space Week has been our one of our events when where we have been doing these space outreach activities. And as all of you know, why we are celebrating World Space Week, to actually remember the major space events, the launch of Sputnik in 1957 and the Outer Space Treaty by United Nations. And that is when in the year 1999, United Nations declared that World Space Week should be celebrated all over the globe, and particularly to establish awareness about space, and all the domains associated with it, and how the space benefits common man and society. So that is why we are here to celebrate World Space Week, and we are really fortunate to have Dr. Jane Blank here today, who will be giving talk on the mission which was launched this year by NASA. And she'll be giving us the broad perspective about this mission. And with that, I request Dr. Vaibhav Raut to officially introduce our today's speaker. And as Vaibhav Raut is also associated with Amity University, and we are pleasure to co-organize this event with so many institutes, as you must have seen the logos. And I must also thank NASA for allowing us to have NASA logo for this event. Thank you, Dr. Jen Blank, and we are really looking forward for fabulous talk. Over to you.
Oh, thank you. Are you going, Wendell? Are you going to say something?
Yes.
Okay.
Okay. So it is indeed a great pleasure to introduce Dr. Jane Blank, whom I had opportunity to interact, where she delivered a talk for Space Geeks in one of the one place in Mumbai, which is social, where she spoke about the connecting Mars and Earth, and it was a really wonderful uh, event which Space Geeks had with Dr. Jane Blank. Uh, Being associated with Amity University and Center for Astrobiology, which is an association associated with the organizing of this talk, uh, I welcome Dr. Jane Blank on behalf of Amity University and Space Geeks. Uh, Dr. Jane Blank is an astrobiologist with NASA at Ames Research Center in Silicon Valley. She is also a senior scientist with Blue Marble Space Institute for Science and adjunct professor at the Astrobiology Center for Excellence at Amity University, Mumbai, India. Her research has focused on water and rock chemistry derived from volcanic rocks that supports microbial life and mineral biosignatures, these life deposits. Currently, Dr. Jain leads the NASA Braille project, a study of life and robotic mission to detect life in volcanic caves. Her team is preparing for a future mission to a lava tube on Mars. Jen has worked as a member of Mars Curiosity rover science team, planning science operations for the CAM laser instruments on Mars. She holds undergraduate's degree in geology and English from Stanford University, a Master of Science degree in oceanography from University of Washington, and a PhD in geochemistry from Caltech. This year, she was selected as a global mentor for the United Nations Space for Women initiative. It is indeed a great pleasure to have Jane Blank today with us. So welcome, Dr. Jane, and I invite you to deliver today's talk. Thank you.
Thank you very much for that introduction, Winbo. And it's really nice to be joining you all virtually, if not in person. And I've had the pleasure to meet some of the space geeks in person more than one time when I visited Mumbai, and had a really nice time just socially, and also talking about Mars, and also visiting the Nehru Planetarium. So I look forward to our next in-person visit. But meanwhile, I'm going to talk today about the Perseverance rover mission to Mars. And my title is On Our Way to Look for Signs of Ancient Life in Jezero Crater. Many of you may have watched all of the launch activity this summer. It was so exciting. And first we had, let's see, excuse me. I just have to figure out how to move the slide. There we go. First we had the United Arab Emirates launched their HOPE mission orbiter to Mars on 19th of July. And that was beautiful and successful, especially to see all of the men and women in costume, or thobes, and mostly men actually in thobes, in their absolutely gorgeous new space center. And then we had China launch its Tianwen-1 mission on the 23rd of July. That was a little different because we had no live coverage. So I actually watched it from someone from India who had a friend with an iPhone recording with a patio view of the launch, and that was very interesting. And then once it was successful, then China released the footage, and so we could see that. And then finally, on the 30th of July, very early in the morning for me here in California, got up to watch the launch of Perseverance from Kennedy Space Flight Center in Florida. And anyway, it's pretty exciting. And it's due to land on Mars on February 18th next year. So just in case you wondered where, or you wonder where the capsule is, it sits in the nose cone of the Atlas V rocket. And once that rocket leaves Earth's orbit, then the cone splits off and the capsule heads on to Mars. So many of you, or some of you, may be watching the progress of Perseverance as it goes to Mars. You can go, you can look online at one of the NASA websites. If you just Google, where is Mars 2020? And it shows you exactly where the rover is in space, and how long it will take to get to Mars, and how far it's traveled. But anyway, here's a timeline of this mission. Now, I show the launch at the left here, but this is actually launched in 2020, but the mission was first commissioned, I guess, in 2013. So it had 7 years to get ready, to select the instruments, define the landing site, build and prepare the integration of the instruments with the robot. And that took about 7 years and before the launch. And now we are here in phase 2, the cruise and approach. So after that, we'll go to the entry, descent, and landing. You might have seen the videos of 7 minutes of terror. We're going to have the same similar sky crane approach to landing on Mars. And then we have our surface operations, which should last 1 Mars year. That's called the nominal timeline, which is about 2 Earth years. Now, Curiosity rover, which I'm still a member of the science team of, Curiosity had a nominal mission also of 1 year. And that was, gosh, over 8 years ago. So it's still going strong. So here's a picture. I love this picture from the Planetary Science Society of the Mars Exploration Family Portrait. You can see circling Mars, all of the different orbiters that have inserted successfully into the Mars orbit, and then also the sort of family of landers and robots. There are actually, let's see, 8, I think, other different landers and robots that have made it to Mars. Starting from the Viking landers in the 70s, and then Little Sojourner in the 90s, Phoenix. After that, 2 of the Mars exploration rovers, Spirit and Opportunity, and then the Curiosity rover that landed in 2012. But so for all of this interesting activity, there's still a lot we don't know about Mars, and Mars, which seems to be the planet most like Earth in our solar system, still has a lot of mystery for us. But I personally think it's the best place to look for life in our solar system. And that's one of the reasons or one of the inspirations for me in my research. So the Mars Exploration Program goals, as defined by NASA, are the following. 1, determine if life ever arose on Mars. Understand the Martian climate, processes, and history. Determine how the surface and interior of Mars evolved. And finally, prepare for human exploration that we hope will happen in the 2030s, either with NASA or other space agencies, or from efforts from the private sector, or perhaps a collaboration. All right, so the evolving Mars mission strategies in terms of what's driving our missions and our goals. First, we heard about follow the water. So look for go to places on Mars where we think there's water in the past. The next was assess the habitability of those sites. And that followed through the Curiosity rover working in Gale Crater. And then finally, now we're back to sending instruments to Mars that can look for organics and even detect life. And so this third strategy is to look for signs of life in the form of past life and biosignatures. So not squirming microorganisms, but actually chemical and morphological signatures that are evidence of past life. So today, we know that Mars is a cold desert. Now, I've been reading with a lot of excitement about the discovery of multiple underground lakes on Mars near the poles, and that's pretty exciting. So we may have large flowing reservoirs of liquid water below the surface, but on the surface, it's very cold and very dry. This is actually a site called Dingo Gap from Curiosity, and Curiosity went to this sandy area here and then had to back up because we were concerned the wheels were going to get stuck. Now, even though Mars today is dry, we think that there's from our observing from telescopes and from satellites, Mars has a lot of evidence that it had liquid water on its surface in the past. And here you have a picture of modern Mars. There are better resolution images online, but also an artist's rendition of what Mars may have looked like 3.6 billion years ago. And this is just based on age constraint from the impact crater record and also from the topography. Here's another picture of that. I love this picture because it points out this Martian dichotomy. And that's, you may have heard that phrase, and that refers to the fact that the northern hemisphere of Mars is much lower in elevation by an average 3 to 5 kilometers than the southern hemisphere of Mars. And so most of the missions to Mars have actually landed in the mid-latitudes or the northern hemisphere, where we can take advantage of the very thin atmosphere, but still atmosphere to help with aerobraking and slowing down the craft that's coming to the surface. This, by using the atmosphere for braking, it means we have to have much less fuel, much less mass, and so it makes the mission more affordable. So looking at the Martian geologic periods, this is from based on the Mars impact crater record primarily, and also from mapping work by Jean-Pierre Bibring et al. And anyway, here you can see the Martian geologic periods. You may have heard of them: the Noachian, pre-Noachian, Hesperian, and the Amazonian. So 3 periods. And the idea here is that at the very end of the Noachian, this is where we had the Mars dried up. So at some point, there's a lot of the big volcanoes were all forming and erupting on Mars near the end of the first half a billion years. And then shortly after that, Mars experienced a very sort of large global scale desiccation event. And then you had, after this process, you had evaporation, and then you see lots of sulfates on the surface. And then you see a dry period, a very long dry period in the Amazonian, where you have a lot of anhydrous ferrous oxides that are seen on the surface. So this sort of simple, simple model for the Mars time periods has really colored our thinking about activity on Mars. We think that Mars was most like Earth in this Noachian period when it was wet and when we had surface water, and then something led to the loss of a lot of Martian atmosphere and drying of the planet. And we have a lot of ideas for what's been happening, including a loss of atmosphere and loss of protection, subcooling of the planet, being further away from the sun, but I'll leave that for another talk. There still remain a lot of outstanding questions about Mars, in Mars science. And here are 3 of the major ones that has to do with: was there ever life on Mars? Or could there be life now? I'm one of the people who wants to explore the Martian subsurface to look for signs of life, because we have not seen any evidence of life on the surface so far. But that said, it hasn't been since the Vikings that we've sent any instruments to Mars that have been able to detect life. What are the details of Mars chronology? Excuse me. This is a picture by Hartman and Newcomb showing the interpretation of, again, the age dates of different parts of Mars, or different Martian surface. And this is tied to the Martian crater record, which is in turn linked to the lunar crater record. So a lot of detailed work has been done, and lunar samples have been dated chronologically, but there's still a lot of questions, a lot of poor constraints on this Mars chronology. And finally, understanding evolution of Mars as a system. What were the element cycles on Mars? Were there ever plate tectonics on Mars? What is the distribution of different gases and light elements and heavy metals on the Martian surface? We still don't really understand a lot of these details because we really haven't explored very deep in Mars, only about 5 centimeters, and there's still a lot of detail to be discovered on Mars. That means there's a lot for everyone to do. So if we think about trying to map that early Mars timeline onto the terrestrial biological timeline, you can look at this yellow arrow. It points to where Mars climate change happened. So, and then this arch essentially is the time. So going back to formation of Earth about 4.5 billion years ago, up to today where we are. And you can see back here on Earth, we have evidence of life on Earth at about 3.5 or 3.6 billion years ago. And that life didn't have a skeleton. That life was microbial life. So evidence is really in the rock record in the form of patterns and geochemistry, so chemical signatures. But there are so in other words, a lot happened on Earth between then and now when we first saw the fossils and during the Cambrian explosion. Those are the first preserved hard fossils that we see on Earth. We see nothing like that, or no morphologies like that on Mars. So we wonder, what happened after the Mars climate change, and why is Mars so different from Earth in terms of its rock record? Now, one advantage of Mars is that because Mars doesn't have active plate tectonics, as far as we know, a lot of the surface of Mars consists of very, very old rocks. And that's quite different than Earth, where we have only traces of old rocks. So here's a picture showing the remnants of ancient continents and their ages. So the oldest continents we know of are up in Canada, and those are dated, actually Canada and Australia, and those age constraints come from dating of zircon crystals in very old metamorphic rocks. But we think that we have records of Earth rocks dating back to almost 4.4 billion years. So that's pretty old, near the time when Earth was, very, very young and forming. But still, these rocks have been altered and metamorphosed. Whereas Mars has more than 50% of its surface has rocks that we think are more than 3.6 billion years old. So it's very different from the situation on Earth. And so by studying Mars geology and surface, we might learn more about Earth's evolution and also how Earth will be evolving in its future. Thinking back to that diagram of the Earth's history, if we're thinking about where to look for life or what to look for in terms of Martian life, well, we might on Earth we might look for fossils. Here are these classic fossils that came about in the Cambrian, but we don't expect to see those on Mars. Instead, we expect to see microbial biosignatures that would be in keeping with those we find on Earth in our most ancient rocks. So here is a picture on the right of stromatolites from the Pilbara region in Western Australia. And this is what they look like in the fossil record. Now, stromatolites are so cool because, well, they're so cool for many reasons, but they exist all over the planet today. And here is a slightly blurry picture of modern stromatolites from Shark Bay, also in Western Australia, where you can actually go swimming with these things. They don't move, at least they don't move on timescales we recognize. And they're just so fascinating to see that these are essentially mounds that have formed by little intricate layers of minerals and microbes, creating mats, and then depositing biominerals and growing up towards the sunlight. Here's another picture of these stromatolites in their context in Western Australia. And these have been dated at about 3.5 billion years old. We have stromatolites that are living in California, in Canada, in Europe, and there must be some in India that I have not visited. Anyway, all over the world, and they're very fascinating. And the microbial communities that help form these things are also very interesting. So we might be looking for something like this on Mars. Here's another picture of that stromatolite from the Pilbara region in Western Australia with the scale of a Sharpie. Essentially, they're growing upwards to the sun because they have a lot of photosynthesizing bacteria. So, but how could we possibly detect this ancient life on Mars? Well, as we're trying to interpret biomineral signatures in the rock record, it's very challenging when we don't have a fossil to pick up and inspect, because the rocks have been affected by their preservation, their deposition, preservation, and often by metamorphosis or metamorphism that has changed the rock shape and chemistry. So what we tend to do on Earth is we use an assortment of characterization. And if all of the lines of evidence suggest the presence of life, that's the most convincing argument that these things are actually biominerals. So here you can see some biominerals on a terrestrial sample, and this is an organic molecule, or we look for lipids and macromolecular materials that are indicative of life. And also we use stable isotopes such as carbon and oxygen that have ratios that would be similar to life as we know it today. So now I'm going to move back to mention this planetary science decadal survey. So every 10 years, NASA commissions, the National Science Mission Directorate commissions a decadal survey. And this is a document and a report that they commissioned from the National Academy of Sciences in Washington, D.C. That helps make recommendations for NASA's next 10 years. So we've just this summer finished submitting white papers and reports to contribute to the next decadal survey. So I think this year during the pandemic, I worked on 9 of these. These are open to the entire Mars community, and anyone in the world can submit one, but it's all on your own time. So you have to be pretty passionate about this, which I am. And then the panel of experts reads all of the reports and then distills this down into community consensus for what the experts think are the most important goals and areas of focus for the next decade. So the current Mars missions and even Perseverance rover really are guided by this decadal survey from the years for 2013 to 2022. And the highest priority from that prior decadal survey was that Mars exploration and sample collecting rover should go to Mars and collect samples to prepare to bring them back to Earth, because we learned so much more we can actually touch the samples. Now it's amazing and fantastic to have these robot explorers on Mars, but really as geologists and scientists, we learn a lot more when we touch the rocks. An example of that is how much we learned about the moon from the samples that were brought back by the Apollo astronauts. Now, some people might say, why do you need samples when we have Martian meteorites? Here are 2 pictures of Martian meteorites. And in fact, we found, and we confirmed this, we decided they're Martian in origin based on their noble gas contents. We've identified more than 250 meteorites that have come to Earth from Mars. Now, these meteorites are fantastic, and they're the subject of much study, but they're all igneous in origin, and they record very little of the surface processes of Mars. And they also lack a geologic context. So we don't know where they came from on the surface of Mars. And they might have all come from a similar spot, which would just be pieces of one large impactor, for example, that blasted off many meteorite bits. So the Mars sample return and Mars science missions seek to fill the gaps in the distribution of materials and our scientific knowledge of Mars by trying to collect samples that represent a range of rock types and a range of depositional histories. So moving on to the science objectives for the Perseverance rover mission. So it's broken down to 2 bits. One is to understand the possibilities for life on Mars. So look at the geology, look for astrobiology, and finally, for the first time, we're going to be collecting samples and caching them in a little repository that will then be picked up by a future mission. So essentially, by selecting the site of Jezero crater and selecting these instruments for the Mars Perseverance rover, we're essentially fixing a site of a future mission to the same location on Mars to pick up samples that we're caching there. And finally, another goal is, another objective is actually to help prepare for human life on Mars with some new technology concepts and testing. So meet Perseverance. So this is something that NASA does in terms of as it marches out its next rover. And what it does, we've seen this with landers. The InSight lander is similar to the Phoenix lander. So we had Curiosity that launched in 2011 and arrived in 2012. That's the team I work with. But we've essentially brought out the same model for the body of the rover for the Mars 2020 rover. And this is something NASA likes to do because we know the Curiosity rovers worked very well. So the technology has been tested extremely. And so we can build on that prior success that also saves so much money and time in the development of a new model. So we can essentially build on that old model with some small improvements and then add a new instrument suite to that model. And here we go, ready to go again. So now I'm going to tell you a little bit about the next, some of the differences and improvements. Well, first, here's you probably all have seen I mentioned the 7 minutes of terror, but the sky crane, which was technique developed by the military to deliver small, or rather large cars to hard to reach areas on Earth. So we use that same sort of technology to deliver Curiosity to Mars, because Curiosity weighed over a ton. And so it wasn't able to use the same techniques that have been used for prior rovers and landers. So with the Mars 2020 rover, we have some improvements. We actually have the capsule coming down and taking photos during the descent. And then it compares to a very detailed orbital map that we have already. And if there are any challenges or any obstacles, the capsule can divert in real time and avoid those. So this allows us to land near the edge of Jezero crater in an area that we wouldn't have been able to land in with Curiosity. So this is pretty exciting. Another improvement has to do with the mobility system, and specifically with the wheels. I love the fact that the Curiosity wheels had essentially holes in them that tapped out in Morse code JPL for the Jet Propulsion Laboratory, where they were made on the surface of Mars. So that was fantastic. But this wheel design on the left, as we saw after about 300 Martian days, these were not holding up very well on the surface of Mars. In fact, they were punctured, they were starting to break apart, and the team became worried that this is actually going to be a consumable, and the mission could be essentially defined or terminated based on how well the wheels would last. Well, so now sometimes we're driving backwards. We have new algorithms for the pressure and the maximum driving speed based on the terrain roughness. So we're still going, but the current wheels on Curiosity look pretty beat up. So the wheels on Perseverance are made of the same material, but they have different treads. They're slightly smaller, and we've done a lot of testing in the Mars yard at JPL and think they will hold up much better. Now, finally, probably the most remarkable achievement, in my opinion, is the sampling and caching subsystem. So I wonder if any of you know that this Mars Perseverance rover actually has two arms. There's a big arm we see outside, which is this right here. And then there's also a smaller arm inside the body of the rover that moves the little capsules around, that caches the samples. So we have this capability to drill down with the arm, a coring drill, put that material in a small sampling capsule, and then move that capsule around inside the rover. So we can pick up capsules and deploy them again. So we can move them around on the surface of Mars, as well as inside the body of the rover. So it's pretty remarkable technology. And here's a little video of the sampling and caching strategy. So here what you see is the landing site where the X is. And then the little blue circles indicate regions of interest, so where we might sample. And we have already targeted regions of interest based on the orbital maps and very careful geologic maps that team members have made. And then we will essentially put samples in little sample tubes and bring them back to one common repository area. And if the mission is extended past that nominal Martian year, we'll be able to go and sample other parts of the Jezero crater region and bring those little capsules back to a common repository site. So with this plan, we have the capacity to collect almost 0.5 kilogram of material, which for scientists, that's just a ton. That's fantastic. And that would be up to about 35 samples. So it's really exciting. It's really exciting in about 10 years. Anyway, and finally, another technology demonstration is the Ingenuity helicopter. And oops, I love this name because I like to misspell it, Ingenuity, but it's actually Ingenuity. And this is, if you're interested in this instrument, or this device rather, there's so many wonderful videos and online that I'd recommend having a look at. This is a two-tiered rotor helicopter, and these are carbon fiber blades that are about 1 meter long, And right now, this little helicopter is tucked up in the belly of Perseverance rover, and it's going along for the ride just as a technology demonstration. Its nominal mission would be to fly 3 sorties of about a minute and a half each, and up to 1 kilometer in elevation, but just show that we can actually fly on another planet. How exciting! It carries a camera, a color camera, and best case scenario, it'll fly many more times than that, but even to demonstrate that it can fly on another planet will be quite an achievement. I'm very excited about this instrument. All right, but now let's go look at the science payload. So here we have the Perseverance rover. As you can see, it looks very similar in some ways to it has the same body as the Curiosity rover, with which I'm very familiar. But you can see there's some heritage instruments that are very similar to what was on Curiosity, and then it has some new instruments. So I'm going to march through these a little bit. You can see here's the arm, and there are instruments on the arm. So first it has this, I'm going to mention this, to me this is exciting. It has the RIMFAX, or Radar Imager for Mars Subsurface Experiment. So essentially it has a ground penetrating radar that can interrogate up to 20 meters into the Martian subsurface. And that'll be interesting to see. Perhaps we can see, with Curiosity we saw, with the RAD instrument, we saw a lot of water forming, and water ice rather, at about 30 to 60 centimeters in the subsurface. And we might see something even up to 20 meters. There might be even more interesting water present there. We have the Mastcam Z. Now the Mastcam's on the mast, and it's been invaluable in helping us understand and look for both targets on the in Gale Crater with Curiosity, and also just giving us context imagery. So here you can see in this cartoon to the right, again, where these instruments are located. And Mastcam Z stands for zoom, and the zoom was descoped for Curiosity. So we brought it back, and this Mastcam has separate zoom capabilities in each of its camera eyes, and they're essentially bug eyes. They can zoom in and out, and it'll give us a great context images, and also take color video. So then we have SuperCam. Now, I think as you heard, I'm part of the ChemCam science team, and SuperCam is even better than ChemCam. SuperCam is ChemCam rather was the first interplanetary laser, and it could interrogate targets up to 5 meters away from the rover. SuperCam is even better. Whereas ChemCam made a small plasma and used LIBS, or laser ionization breakdown spectroscopy, to look for elemental abundances that were formed in the plasma. So when the plasma cooled down and emitted light, a detector on the body of the rover could identify the spectra corresponding to essentially the spectra that matched with the light that was emitted from the cooling plasma. And SuperCam has that same LIBS capability with higher standoff distance, 7 to 12 meters, and also it has a Raman spectrometer. So this will give us, and then plus an inline context imager. So ChemCam had a remote microscopic imager, an RMI. SuperCam has the same thing. Here up on the right, you see a picture of, this is one of the first drill holes in Yellowknife Bay. And you can see this drill hole is about 5 centimeters deep. Oops, excuse me. And you can actually see the points if you look of where, oops, trying to get my little laser pointer back in, where ChemCam did a profile down the drill hole. See where those red arrows are. And then was able to show the RMI picture for context to see the drill holes. And then in the image B, the Mastcam camera also took a picture of that image after that, and you can see it actually in high resolution, showing actually the raster of the ChemCam. So SuperCam will be even better, and we'll be able to include Raman spectra images, so images that will tell us about chemistry, not just elemental chemistry, but functional group chemistry and organic chemistry at atomic and molecular levels to give us more detailed information about the composition of targets from a standoff perspective. So whereas ChemCam was a super scout because the rover could fire ChemCam while it was driving, we don't usually do that, but it's possible. It also takes very little energy, and we fired over 700,000 laser shots on Mars with ChemCam. And so you get a lot of data for low power, and it becomes a data processing, data mining exercise. SuperCam will have that sort of capability with higher standoff distances and coupled with co-aligned Raman spectroscopy, which will tell us about organics and functional groups. That's really exciting. The Raman was actually descoped from the Curiosity mission too, but again, since we didn't have to rebuild or reinvent a new rover design, we had more resources to devote to more complex instrument payload. So now we have the PIXL, or Planetary Instrument for X-ray Lithochemistry. And this is exciting. This is on the arm of the rover. It gives us microfocus X-ray fluorescence. That gives us elemental chemistry at very, very fine scale. So this instrument doesn't touch the target, but it's on the arm and is only a few millimeters to a few centimeters away from that target to give us very, very close at sub-millimeter scales information about the target. And here's some pictures showing just some context. Look, here's a visible image showing a contact between a conglomerate and a mudstone and an alteration vein or a chert. And we see these different, the color combinations rather represent the different element abundances. And you can see how they correlate with the visual, rather correlating the chemistry with the visual, and sometimes having new chemistry that doesn't show up clearly in the visual. So we can find out, or rather we can find out a lot of things by having these multiple prongs of interrogation for close samples. Next, we have the SHERLOC, which is also on the arm. It stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. And I think, for the astrobiology scientists, this is one of the most exciting instruments because it's going to give us capability to look for organic compounds. So we're using deep UV in the Raman and fluorescence spectrometers to look at, again, sub-millimeter scale or sub-100 micron spot size to look at this mineralogy and organic correlation. And going back to thinking about the stromatolites, there we had the layers. I mentioned we have layers of minerals and organic compounds. So this is really designed to look for that sort of scale and morphologies of features that we see from the earliest life that we know of on Earth. So it's preparing us to look for those similar types of features on Mars. I hope we find them. We also have SHERLOC, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. So here's SHERLOC actually will be able to look for light elements as well. So that's another Raman spectrometer and fluorescence spectrometer. It's going to be very exciting. You can see it's also on the arm. So we're going to have all these co-located, highly focused chemical and geochemical probes for looking at targets in detail. Along with SHERLOC, of course, is Watson. It's a camera to give the context information about the geochemical probe data. Watson stands for Wide Angle Topographic Sensor for Operations and Engineering. It's really based on the Mars hand lens imager, or the MOXIE instrument that was on the arm of the Curiosity rover. In this case, it's color, and it's integrated, rather co-aligned with the electronics within SHERLOC. So it'll give us, again, that context information. So as I mentioned, these instruments will all work together to give us detailed camera contextual images, chemistry information, and we hope that the best, or we expect rather the best detailed information about the mineralogy and the organic geochemistry that's present on the samples on Mars, or on the surface of Mars. Watson was also, since the camera on the arms, also going to be able to take selfies of Perseverance. So just like this is a selfie of the rover at Bagnall Dunes and Gale Crater. It was taken with the MOXIE camera and essentially a composite picture of about 50 images from MOXIE. So we'll have the same, don't worry, selfies are not going away. We're going to have lots of selfies. They're some of the most popular images that we've sent back from Curiosity, and we'll be taking a lot of selfies in Jezero Crater too. Now I'm going to move on to two of the instruments that are part of the package, but focus more on future human missions to Mars. We have this MEDA, or Mars Environmental Data Dynamics Analyzer, to look at the suite of environmental sensors to monitor the weather on Mars, essentially, and looking at 6 parameters: the wind speed and direction, the pressure, the relative humidity, the air temperature, the ground temperature, and the radiation in discrete bands of the UV, visible, and IR ranges of the spectrum. So essentially paving the way for how to make it safe for people to live on Mars. And then another, I think, a really exciting instrument is this MOXIE instrument that stands for Mars Oxygen In-Situ Resource Utilization Experiment. And this is really, it's a proof of concept experiment to take CO2 from the Martian atmosphere and convert it to oxygen for 2 reasons. One is to be able to make propellant, because it's very expensive in terms of the carrying, very expensive to bring mass to Mars from Earth. So if we want to return to Earth from Mars, we would like a way to generate propellant at the surface of Mars. So that's one of the applications of this. And the other one is, of course, is to generate oxygen for people to breathe. So essentially, this is an electrolysis instrument. Sucks atmosphere and releases oxygen in the exhaust. So think of it as like a mechanical plant. Not an industrial plant, but like a green plant. All right, so I've sort of run through the different sample payload, the instrument payload, and I just want to mention that the Mars rover evolution has really transformed from the early days of the Sojourner, which was a small shoebox size rover that just went a few meters away from the lander to study the bulk geochemistry of the nearest rocks and no sampling. The Mars exploration rovers, which had tools that could scrape so they could abrade the surface and look at bulk geochemistry, the mineral geochemistry, to MSL, where we've I think drilled 24 holes, is that, or 27 holes, sorry, 27 holes within Gale Crater over the past 8 years, and then brought that powder on board to be processed by 2 very complicated instruments inside the body of the rover, the SAM and ChemIn, to look for the bulk geochemistry, organic geochemistry, and actually take X-ray patterns to determine for the first time the actual stoichiometry of the minerals we're seeing. But in all of these cases, the sampling and the interrogation is supporting our exploration. And now with Perseverance, we're really moving on to a new phase of exploration, where exploration is supporting sampling. So this is a multi-phase endeavor here. So we have, with Mars 2020, big emphasis is going to be on the coring and the caching, and getting this spatially resolved geochemistry and mineralogy and organic chemistry information to essentially help detect the best samples to cache for future retrieval. So the Mars 2020 scientific exploration model is, just to summarize again, is to develop context of an ancient Martian environment using observations made at a range of spatial scales, culminating in a search for potential biosignatures. So we're going back to looking for life in the ancient rock record of Mars. And then use the emerging geologic model to guide the collection of samples that maximize opportunities to understand Mars as a planetary system and determine whether it was once habitable. So these pictures are mostly, well, the combination of, this is from Gale Crater looking toward Mount Sharp, as you might recognize, but here are once again, our Mastcam heritage instrument on Perseverance, the ground penetrating radar, the RIMFAX. This is actually a dust storm or sandstorm on Mars, but we have a weather station on Perseverance. We have SuperCam, we have Watson and PIXL and SHERLOC on the arm, and then we have this drilling capacity, much more refined drill than Curiosity had. Perseverance will be able to drill deeper and drill rather than have a percussion drill that Curiosity had. So it's a very exciting payload. And once we essentially instruments were tested, and actually at the end of this presentation, I took out a video showing all of the tests, or a summary of all of the testing they did, because some people ask, why are these instruments not more sophisticated? Well, we have to, NASA is very cautious about preparing instruments to send on a planetary mission. So they might not represent the most modern technology, but they represent very robust platforms and instruments that can withstand that voyage to Mars. So they have to withstand a vibration test, they have to withstand exposure to vacuum, to radiation, to large temperature variations. And once they pass all that, they get stacked up together. And here this image was taken this year during the pandemic at Kennedy Space Center, right before the capsule was shut up, rather the rover was shut up inside the capsule. Next time this shell will be open is when the rover and capsule land on Jezero crater. So as of last night, we're about 41% of the way to Mars, and we'll again land in February of next year. So I encourage you all to go online and check out the location of the cruise rather. And once we get to Jezero, our scientific adventure will begin. So here's just a review of the prior NASA landings on Mars. You can see where Mars 2020 is in relation to the other ones. It's here right in the low latitudes. And once again, focusing in on the Perseverance landing site, Jezero crater. This is an elevation contour map showing once again the northern part of Mars is at lower elevation than the southern part of Mars. And just as an aside, I'm currently working on a mission to volcanic caves on Earth in preparation for, as of yet, not selected mission to Mars, but we're gearing up for that. And most of the volcanic caves that we've seen from orbit are in this higher latitude or higher elevation regime of Mars. And so we're actually excited that the engineers have been improving their landing capabilities and actually have strategies and they believe capabilities for landing at this higher elevations where we see this big volcanic terrain, or the broad volcanic terrain, excuse me. All right, zooming in on Jezero crater again, you can see it's at the edge of this acidus impact basin, which is dated to be about 3.9 billion years. And it's very small, it's about, well, Jezero is small, it's about 50 kilometers in diameter, so that's considered small. Now, Jezero crater was selected from many candidate landing sites, and the community, the Mars community from all over the world, advocated for different sites and narrowed it down to 3, and then marked that the selection of Jezero was made at NASA headquarters. And here's another picture of Jezero showing some of the features of interest. So you have this inflow or inlet valley, and you can see this big deltaic fan here. And then and then you have an outlet. So there's a flow in, an outlet channel, and the basement rock is basalt. And this is the landing ellipse for the Perseverance rover, hoping to land right near the edge of the primary target, which is this delta. So there's a blow up. I show you the landing ellipse. Then again, this picture of the delta for Jezero crater. And this delta has been mapped in detail based using the data from the Mars orbiters, especially the HiRISE and CRISM instruments that give us mineralogy and chemistry. So you can see here's a map overlaying on the delta, showing that they have clays are present, I believe, carbonates are present, and mafic minerals such as olivine. So we want to, this area gives us a sort of good representation of different rock types of interest on Mars. Also, materials that might help, might preserve organic material. When deltas form on Earth, they're usually, they tend to bury organic material rapidly. And so we think that this rapid burial might increase the chances of preservation of organic material over time. So here's a river delta picture from River Delta in Alaska. I've actually been here. But they are habitable environments. And you can see there are many, there are many braided streams in these deltas. And we see similar features when you look in detail at Jezero crater. Now, with respect to Space Geeks, I want to just throw up this picture of Lunar crater, because it turns out that India has one of the best analogs for Jezero crater on Earth. And by that, I mean that we have an example of an impact crater into basalt, host rock. This is very rare on Earth. The other ones we know of are smaller, and they're up in Siberia or in the jungles of South America. And this crater, though, is very small, only about 1 kilometer across. And it's Lunar crater in about 4 hours by train from Mumbai. And it's only about 50,000 years old, so it's very young. But it does have, people, people and animals are using the crater, but it does have this sort of similar deltaic fan. And when in drier times, you can actually see, evidence of the braided streams and channels. Another difference, aside from the size and the age and the people, is that there's no outflow. There's no outflow for Lunar crater. So what goes in essentially stays in, or evaporates the water that comes in. And this crater is about 100. Rather, the lake that's in the bottom of Lunar crater is about 150 meters deep. So it's a very shallow lake in the center. There's no real perfect analog on Earth for sites on other planets. So all of the analogs have good things and not so well matched aspects of them. But Lunar crater, by being an impact crater into this basalt, is very interesting. And I know Chinta's studying some of the impact breccias and the mineralogy of those to better understand the formation history of this impactor. And actually, I've been on a scouting trip with some other people from Amity University to look, to essentially prepare and create a strategy for trying to sample across the delta in sort of an analog mission scenario that would be suitable for a comparison with Jezero. So I'm getting near the end of the talk, but I just want to show you this potential mission scenario for Jezero. So there are two little plots, or rather two paths here, and you can see if we land, one option might be to go look at the delta remnants in the eastern part of or further away from the eastern side of this landing ellipse. And this is about a 15-kilometer traverse. And an option 2 would be to go west and look for, actually go on to the delta and look for sample locations of the delta, and then move closer to the crater rim, another 15-kilometer traverse. And the boxes here are areas, again, that have been targeted as keen sites of interest for sample collection and caching. So the cool thing is that in this relatively small range, which are about 15 kilometers, we have a lot of different rock types and a lot of different potential for expanding, vastly our understanding of the geology of the Martian surface. Now, when I say 15 kilometers, well, Curiosity in 8 years has traveled about 19 kilometers. So maybe that's a longer distance than you might think. It's not that the rover can't travel fast, it doesn't. We get distracted. Anyway, and then here's some potential Mars 2020 sample cache composition. So if I take those boxes from the last slide and look at the types of rocks we might find this mafic floor, which would be typical of a surface, or rather a basement deposit on Mars. Or we might find olivine, carbonate-bearing materials. We might find distal delta lake deposits, and that would have different geochemistry than sort of more interior delta deposits. We might find regolith from Jezero crater itself. Then we'll have blanks, of course, with nothing, not my personal samples, but actual blanks. We might find other features such as point bar deposits or inverted channel deposits or other lake deposits. And then finally, crater rim or deposits with evidence of shock history that would help us better characterize the energy and the type of impactor that created the Jezero crater. So just to finish, the return sample science objectives are as follows. Life, so determine whether fine-grained Loa delta strata and carbonate-bearing units contain biosignatures and show evidence for past Martian life. Geochronology, try to figure out the age of the basement materials in this Jezero crater and also some other rocks. Look at the crater chronology, try to understand the relative, to really pin down the ages of the different units within the crater. Look at the igneous history to understand from the mineralogy. I mean, again, once again, we're going to have really detailed mineralogy. And from that, we can infer a petrogenesis of the mafic floor unit, and that'll be very exciting. Look at the carbon cycle, start to do that by having all of this organic chemistry data that we'll be able to collect with onboard instruments. That'll tell us more about how the delta formed and how the delta evolved. Look for the lake chemical evolution. We think this delta flowed into a lake, a very shallow lake in Jezero crater. And finally, understand better the early Mars climate, because we think that Jezero crater has very old rocks to, when the time, obviously when Mars was wet, and up to the time when Mars was dry. So that Amazonian Hesperian transition and Mars geologic timeline. So that said, this is Mars 2020, but this is really part of a notional 3-mission Mars sample return campaign, which is going to suck up a lot of the NASA's Mars funding for the next 8 years or so. So we're here, we have Mars sample collection, Mars 2020 starting next year upon landing. And then there's a scenario for a Mars ascent vehicle, which will launch these samples that will require another lander to come. And then finally, the Mars orbiter will capture these samples and bring them back to Earth. So it's pretty exciting, and it would be amazing to have these samples, but in the meanwhile, we'll have to wait and wait and then get ready for the time when one day we can actually be in the same room with samples that we have, not an impactor, but we have brought back from Mars. And so with that, I'm going to conclude and say, I want to say thank you to Dr. Katie Stack-Morgan, who's the Deputy Project Scientist for the Mars 20 mission and a friend of mine. And she shared some of these slides with me. And also I wanted to put these links up. So take a screenshot if you will, or look online, because there's a lot of information at particularly these sites about the mission. Both at the Mars headquarters site and at the Jet Propulsion Laboratory, or JPL Mars site. And finally, I would really recommend looking at this cool website called eyes.nasa.gov, or eyes.nasa.gov. It lets you look for all the missions in our solar system that NASA has currently underway, including the Voyager missions, and you can see exactly where they are, and just see where they are relative to planetary bodies and comets and asteroids and our sun, and it's pretty exciting. So with that, I will finish and I guess take questions or whatever you want to do next, Space Geeks. Back over to you. Oh, sorry, I have one more thing to say, and that is after this talk, I guess, and Chinta, I'm going to put the slide up and maybe let you take over from here.
Yeah, so as we are celebrating this World Space Week, so Dr. Jane Blank has even officially inaugurated the audio talk, which we are going to soon upload as a part of World Space Week. This talk is by Dr. Robin Catchpole, who is associated with Institute of Astronomy, Cambridge, UK, and who will be talking about the astrobiology aspects, and with the title Are We Alone? So we officially thank you, Dr. Jane Blank, for officially inaugurating this slide. And thank you very much for such a fabulous talk. I think I'm going to just watch it 3-4 times and many more to, to understand so much information, and I'm going to bombard you with a lot of questions. So with that, I think forum is open for question and answer session. And
Yeah.
we would, since we are also having the logo for Space for Women, I request Bhumika, who is probably the youngest participant among us right now, and we will start with her question. So Bhumika, are you there?
Should I stop sharing my screen?
Yes, that will, we can have a participant's view.
Okay. Yeah, good.
Bhumika, are you there? Because she has already posted a question I saw, and she's youngest.
Oh my gosh, there are 83 comments in the chat. Oh my God. That's great. I apologize, I wasn't paying attention.
No, don't worry about that. We'll take care of the comments, and we'll put forward the questions to you.
Yeah.
I think Bhumika probably might be having
He has been
some issue
attending
with her
all,
connection.
and it's really good to see that such a young participant was attending all the talks. So I thought,
Yeah, she's just 11 years old.
yeah.
Oh, fantastic.
So
Okay, so we'll start with her question, Chintan.
posted, Virendra.
Yeah, so yeah, I'll start with the question. So just a second.
Yeah, she's
so
joining.
Bhumika had asked, oh, she's here. Bhumika,
can you go ahead
can
with
you
your
unmute yourself and ask question?
Yes, sir. I was having that question that in Mars, what we can get things. Actually, we can get things elements in Mars.
So,
Hello.
yes, hi. So the question is, what can we measure on Mars? Is that what you're
Yes.
asking?
Yes.
Okay, so it turns out it's easier to measure the geology or the elements that make up the rocks than it is to measure the kinds of minerals that are present in the rocks. So the earliest missions to Mars looked for the rock, just straight the elements. So iron, for example, or magnesium, but it doesn't tell us how those elements are, I guess, assimilated in the rock. So different minerals have different chemistries, right? And so it wasn't until the Curiosity rover, the last mission to Mars, that we actually were able to bring powder, so make powders of the rocks, bring them on board to the rover, and there's an X-ray instrument or an X-ray diffractometer that looks at the X-ray patterns of the rocks or even of the powders, because they're very small, and all the minerals have different X-ray patterns. So from those, they're able to tell the proportion, like how much, and exactly what minerals we see there. And they're actually the cool thing is they're very, very like minerals we see on Earth. And that was one of the exciting things about, one of the exciting discoveries about the Curiosity mission, which we see that these are rocks we see on Earth, and they're rocks we see in lakes that form in the bottom of lakes that would have water associated with them that we could all drink. So that was the first time we found that. It was really cool.
Thank you.
Yeah, sure. But Mika, you're the perfect age to be one of the first people to go to Mars. I'm kind of jealous.
Virendra,
Okay, yeah.
take care of questions. Yeah.
Yes. So the second question is by Tanvi. Was Mars the first object similar to Earth, as there were lakes of water found?
Was Mars very similar to Earth, since there's so much water on the surface, right? Lakes and shallow seas, perhaps. Well, we don't know. This is one of the mysteries, but we think, we look at Venus, and Venus doesn't have water, and the surface doesn't have evidence of water. So even though Venus is very close in size, it's closer to the sun. So we talk about the Goldilocks hypothesis. And was Venus too hot and Mars is now too cold? But in the early history of our solar system, the sun was cooler, right? There was a fainter sun. So there's a paradox there, because how could we have it be cooler and yet have liquid water on the surface of Mars? So this is actually a challenge for people who study early Martian climate with very few constraints. And we hope to improve those constraints as we get more and more information about the geology of the rocks that were present when we think these water features were formed on the surface of Mars. So it's not really an answer to your question, but based on the orbiter and telescope images, we think that Mars had a lot of water in that first 500 million years of its history.
Okay, so the next question is by Dipanshu. What made NASA decide to land in Jezero crater rather than near, say, polar regions where there are more chances of finding water?
That's a good question. Why doesn't Mars go? Why don't we go to the poles? Well, short answer is that because the engineers won't let us. So, the scientists get all excited, but ultimately it's the engineers who say yes or no. And right now it's very hard for us to land at the poles. So one of the Viking landers landed pretty high latitude, and Phoenix lander was pretty high latitude, but still nowhere near the poles. So that's the short answer. I hope one day we will go.
May I call Mr. Srinivas to ask his question? He's a renowned space journalist who is present among us.
Sir, unmute your
Sir,
mic.
your mic is on mute.
Can you
please unmute?
your mic? Yeah.
Okay. Now can you hear me?
Yes.
Achha, my question is, what will be the difference between the 7 minutes of terror of Curiosity landing and Perseverance landing on February 18, 2021? Will there be any difference?
Mars might be slightly, Mars has an eccentric orbit and Earth has a more round, a circular orbit. So there might be slightly difference. The 7 minutes refer to the time it took for the information to get transferred back to, or transmitted by radio signal back to Earth. So that might be a tiny bit different, but we think our landing techniques have improved since the last time.
Yes.
So maybe I think it will still be a 7 minutes of terror, but maybe it'll be slightly less terror if that's possible. but it's always scary. Are you kidding? People have poured their heart and soul and billions of dollars into each mission. And we want everyone to succeed.
I'm sure it will succeed.
Yeah.
Thank you for answering.
Yeah, Virendra, go ahead with other questions.
Virendra, you have to unmute.
Sorry, I had a connection fluctuation. Yeah, so I'll go for next question. So Karan is asking, how would Perseverance rover would test or collect water and soil samples?
Okay, how would the rover collect water and salt samples? Well, there is no plan to collect actual liquid water because we don't think it's there. So it would collect water and salt in the form of the rock samples. So it's going to drill down, and if there are excuse me, discrete salts present, it would collect them as part of that drill core and put it in the cache. Put it in the capsule. And the capsule is a few centimeters long, and it's sealed. And it's sealed in a way that it will stay sealed to go all the way back to Earth. So it should be preserved very well. That's a good question. Okay. And water present would be trapped in the form of some sort of stoichiometry associated with the minerals. So as hydroxyl or molecules of water in the mineral stoichiometry.
Okay, so the next question I think is inspired due to the COVID situation. Regarding these stromatolites, didn't virus affect stromatolite formation in the ancient times, especially when stromatolites dominated the shores of the world?
Did viruses affect stromatolites?
Yeah.
I don't know. I don't know. In fact, I don't know of any work where people have studied viruses and stromatolites. They may have done, and that would be an interesting topic because viruses, by our definition, are not alive. but because of that, they might be more resistant to degradation. We
So,
just, I don't know. I'd love your opinion.
As a extended question to that, have there been any sort of studies that you know of where they have looked at the effects of, say, viruses on fossils or animals which are sort of preserved in either amber or say this permafrost or snow, something like that?
I believe they have identified ancient viruses from permafrost, but that's very young, right?
Okay.
So these rock samples are billions of years old, and I don't think we have any evidence, or I've never read of any evidence of enough evidence in the geologic record on Earth of the oldest materials to even well, we see, for example, I mentioned a geochemical signature or an isotope signature. We don't have enough information to have any sort of genetic information that we're extracting from the rocks. So these are really cool questions, and if there's information out there, I'm not aware of it, but I think also just the preservation possibilities on Earth and on Mars too would be such that we're not going to be able to extract like RNA or DNA from material to be able to discriminate a virus or a microbial cell. I hope we find that in the subsurface.
So Arpita, thank you for that interesting question. She has another question. Are the Martian meteorites enstatite chondrites in nature or carbonaceous?
Well, the most famous carbonaceous chondrite from Mars was the Allen Hills, right? I mean, it's a carbon-rich meteorite. But as I mentioned early in the talk, most of the meteorites we see from Mars are igneous, and so we call the class of meteorites that has a lot of carbon. By a lot, I mean up to 15% by weight carbon or carbon material. We call those carbonaceous chondrites, and we think those represent the earliest or the most primitive pieces of material in our solar system. So when we actually model differentiation of planets or even of Earth, we often use that as a starting point for the chemistry, for the geochemistry. Say, oh, the bulk composition of the Earth was that of the most carbon-rich carbonaceous chondrite, but it's not. It's very different from a Mars meteorite, and so we think the Mars meteorites are mostly igneous, sort of volcanic in origin, and or rather not volcanic, but igneous rocks, and so they don't contain much carbon at all relative to a carbonaceous chondrite.
The next question is by Dipanshu. Did we ever find presence of stromatolite on Mars, or probably any other kind of life signature?
No, we have not. We have not, and we talk about how our search for life in the solar system is really biased by how we perceive life on Earth. So when I mention stromatolites, it's because that's the oldest record of life we have on Earth, and those rocks on Mars are really old. So we think that would give us the best sort of target to look for something. But we have not seen a stromatolite. We have not seen any morphology indicative of a stromatolite on Mars, and we hope that will change. We are optimistic, or rather, some of us are. Some people think Mars is dead. They want to go to Enceladus.
So next question is by Joe. Is there capability of living on Mars, or will it not be possible? And I'll probably add another question to that by Subrat. Pragmatically, what would be the key challenges to terraforming of Mars?
I think that there are many people on this call who might be able to discuss that as well as I could, because could we live on Mars? Right now, we would be very vulnerable on Mars. And right now, we don't have an ability to return if we sent someone to Mars. So right now, a space agency is not going to send people to Mars on a one-way trip, right? But I think in our lifetime, we'll be able to do this. And but personally, I would go to a Martian cave, because my biggest fear about Mars would not be having something to breathe. It would be having protection from the solar radiation and for coronal mass ejections. So I would want to go underground and be protected. But in terms of terraforming Mars, actually, I think it's next week or the week after, there's the Mars Society meeting. And this year it's a virtual meeting and it's free for everybody. So if you're interested in humans to Mars and activities and a lot of discussion and thinking about what it will take to have humans living on Mars, I would really recommend or encourage you to Google the Mars Society and tune into that meeting later this month. So how's that for not answering the question? No, it's a fascinating topic.
Yeah. So Joe has another connected question. So when are we going to land on Mars? I think it could be in terms of Perseverance rover as well as humans in general. So what would you like to comment on that?
Well, right now the Perseverance rover is landing in February, I mentioned. I think February on Mars. And then I don't remember, I don't know the date of the Chinese, Tianwen-1 is going to Mars, and that they have actually a lander with, I think, a small rover inside. So I don't remember their landing date, but they left a few days earlier than Perseverance did. So maybe they'll be landing at the beginning of February. I'm not sure. And after that, ExoMars, the Rosalind Franklin rover, was delayed because of the pandemic. So its launch date, which was supposed to also be the summer, was delayed for 2 years. So that will be the next visitor to Mars that I know of. In terms of humans to Mars, there are no plans. There's discussion and anticipation of trying to send humans to Mars in the next decade. But so far, that's just a notional plan. There is no plan that I know of. Does anyone else in the audience know of a plan?
Okay.
Okay.
Elon Musk, right?
Interesting.
the big rocket.
So the next question is again by Dipanshu. So he's asking, keeping in mind the sandstorms that are there on Mars, so what are the chances that the sample return mission will find all the sample tubes at the same place, Perseverance? And is there any possibility that the helicopter might drop it, something like that, if there is a storm? Or can it be damaged?
Would the helicopter fly if there is a dust storm on Mars? Well, that's a good question. And I think for me, the biggest worry would be the dust storm actually might help the helicopter loft. But the biggest thing would be to have that dust get in the moving parts of the rover. Mm-hmm. So that if the helicopter is sitting on the surface and there's a dust storm, it might be blown over. But one thing to bear in mind is, I don't know how many of you seen the movie The Martian, which I loved, but the force of the winds on Mars are not strong enough to throw away that whatever the telecommunication device or the radio communication antenna, as they showed in the first few minutes of that movie. That aside, I love the movie, but we have to bear in mind that the atmospheric pressure on Mars is, the gravity on Mars is so much less, and so the force of these storms are not going to be enough to blow a person over. Whether or not you could blow the helicopter over, I'm actually not sure, but they're just not going to be as extreme as we think of on Earth.
The next question is by Rohit. How much time is taken by radio telescope to receive messages from the rover?
How much, you mean how much time in terms of how long does it take, or how much? Okay, so we have relay systems in place. So each rover has a radio communication link, and it has redundancy. So it has more than one way to communicate with Earth directly, but more importantly and more often with some of the satellites that are orbiting on Mars right now. So in the case of Curiosity rover, we communicated with the MRO, with more recently with MAVEN, with all of the orbiters that are in the sky, right? And so it's very common that for example, the ExoMars mission inserted when they had their test landing with Schiaparelli, that crashed upon landing. They, at the same time, they had a very big success because they inserted an orbiter within orbit around Mars, and that's supposed to again help. These orbiters have a finite lifetime, but it's supposed to help relay information. So we monitor very closely how frequently the orbiters pass above the rovers or landers, and so we can time uplink and downlinks with our operational activities on Mars, and that helps us communicate both commands and also data that we're sending from the surface of Mars back to Earth.
Okay, next question is by Tushar. Is asking what would be the duration of the mission and what were the difficulties NASA faced while planning of the helicopter which is accompanying the rover, and what would be the limitation in
Virendra, I think your some network issue. Vaibhav, can you repeat the question?
I'm sorry, there was some fluctuation on my side. Yeah. So the question was, what would be the duration of the Perseverance mission, and what were the difficulties NASA faced while developing the helicopter for which is accompanying the rover, and what would be the limitation in bringing Martian soil to the Earth?
So in terms of the we call it nominal, which NASA loves to use the word nominal, which means if nothing goes wrong, what is the basic what's the basic definition? So if something is nominal, it means it worked, nothing went wrong. So the nominal mission for Perseverance is 1 Martian year, which is just about the same as 2 Earth years. Now, that was the nominal mission length for Curiosity, as I mentioned, and we've surpassed that. And so what typically happens from NASA is that the team can apply for a mission extension. So we're in our fourth mission extension for the Curiosity mission. But every time there's an extension, we get less money. So that means that people like me have less and less time to devote to that mission, but the rover's still working. So that's exciting. So the nominal mission for Perseverance is 1 Martian year, or about 2 years of Earth time. And we hope it'll go for a long time. It has a radioactive power source, and it should continue. And in terms of bringing the soils back to Earth, once again, this has never been achieved so far. So we are going to cache that material, and we don't even have a mission slated to go to get that stuff. So this is just right now, it's still an idea that we will learn so much more. The community believes we'll learn so much more from being able to analyze any sample in an Earth laboratory that can be so much more sophisticated, right? So we're going to put those materials in a sample caching or sample container and put them in a little repository and pick that up in the future. That's one of the most innovative, this sample collection and caching system on the rover is one of the most innovative aspects of the Perseverance rover assembly. It's phenomenal. I'd really encourage you to go look on the NASA website if you're interested in more details. That's really cool. Was there another part of that question, or did I get everything?
Yeah, you have covered everything.
Okay, cool.
So Sadaf is asking, in MOXIE, after splitting carbon dioxide, what will happen to the carbon monoxide, and how will it be taken care, or will it be released in the atmosphere?
It will just be vented. So there's a step where it goes over like an anode cathode electrolysis converter. It splits the CO2 from the atmosphere, and then it goes through a purification stage where it splits off that like CO or any other residual material, and then pure oxygen comes out for use either as a propellant or as something for us to breathe.
Okay. So how much is the technology gap as far as the challenge of terraforming Mars is concerned?
What's the technology gap? That's a huge question. I think right now, if we can create a bubble or a dome or someplace where people could breathe, that would be like a microcosm of terraforming. And we're working on this kind of question, not for terraforming the entire planet, but for generating breathable atmosphere, even on the moon, right? For extracting oxygen from lunar regolith. So we don't know how to do this yet, right? So I think MOXIE will be a big step in seeing how we can generate, both propellant, of course, but also atmosphere so people can survive on Mars and not have to bring more atmosphere for them to breathe. So it's exciting. And I didn't answer your question, I apologize, but I don't think we know yet. Yeah. So maybe you could figure it out.
Okay, so next question is, how deep can the Perseverance drill the hole?
How deep? I think it's 1 meter is the maximum. But you saw those, yeah. But you saw. I might be wrong though. I'd have to. It's kind of embarrassing. I don't remember exactly. But you saw those. The drill cores are much longer than the small containers, which are several centimeters. So we'll take a section of that drill core and put it in the repository.
Okay.
I think the Rosalind Franklin can drill 1 meter.
Okay.
Is that right, or is it 2 meters? I can't remember.
So Dipanshu has this question: why Lonar has abnormal magnetic field, and why the water is extremely alkaline?
Why does Lonar have a weird magnetic field signature? That probably has to do with the impact history, the fact that it's an impact crater, right? It might represent also the composition of the impactor. If it was a metallic asteroid. And maybe someone on this channel can answer that better than I can. But in terms of why is the water alkaline? Well, it has to do with the fact there's no exit path for that water, and also the host material is basalt. So when you put water in contact with basalt, it is actually should be alkaline, right? So it has unusual chemistry because it's sitting on top of walnut basalt, and then the sediments from the Deccan basalts have come in. So it definitely has some really, really unusual biochemistry and microorganisms that are in the Lonar Lake. And maybe, I think it was in the news this was in January that showed how pink the lake was?
Yeah.
It's just beautiful, yeah. I've been there, I was there I guess it was the month of November. And it was not pink, but I would like to go back when it's pink. Does anybody on the channel have a better answer to that? Why is there a high or an anomalous magnetic signature at Lonar?
Chinta, can you answer something on that?
At Lonar?
Yeah.
One thing is because of the impact, the original magnetic minerals, which were part of the original basalt, because they undergo the different dynamic phase change in the temperature and pressure, and there are also papers which talk about that even impact actually preserve the directionality. So in fact, if one analyzes the magnetic signatures in and around Lonar, there is a possibility one can even find the directionality through magnetic signatures at Lonar, because the way shockwave propagated and it actually deformed the magnetic minerals, apart from the direct melting and then cooling. So I think
that's
important.
Raghavan, were you going to say something? Otherwise, I was going to say that we that's a good point, Chinta, that there's the magnetic orientation of a rock is set or fixed based on when that rock cools. So for a basalt or a terrestrial rock, it's something around 650 degrees Celsius, and then you can't reset it. So when you have an impactor that takes the temperatures up to thousands of degrees Kelvin, and so the Deccan traps or the host rock for Lonar are rocks that are 650 million years old. So they had whatever those rocks were set at that time, and then when the impactor happened about 50,000 years ago, it set the temperature, the rocks experienced a really extreme temperature, so they reset the magnetic signature of that local area to whatever the magnetic field was at the time. And we know on Earth we have magnetic reversals and wobbles, so it's not surprising that it would be different 50,000 years ago from where it was 650 million years ago.
Okay, I have one more question to Dr. Jane Blank, since we are talking about the impact. So, because of the impact, I mean, are there any specific sites of interest where we might feel that there is a presence of, microbial life or, life in the lower form? Because the original impactor, if it is carrying some life material, or, on whether when it gets because of the impact, when it is like around the crater. So from that perspective, any specific sites where are chosen around the crater?
You mean sites on Mars? Or sites on
Mars?
On Mars. Well, Chinta, you've addressed a topic of this sort of near and dear to me. I have two comments about that. One is that we see that there's evidence of these, these larger, or these impacts actually generating hydrothermal systems that are short-lived, on the order of 100 years of time. So this could be a way to get water flowing, and could this support microbial life, or could it lead to origin of life, right? And there are actually people who've studied life and how life changes as you move away from older impact craters on Earth, and hypothesize that this could be, one, essentially, it's short-lived, right? So it's a sort of, the time scales are similar to hydrothermal vents that last on the order of 100 years. But could this be the energy gradients and the liquid water and the metals and organic compounds, could these all be, essentially concentrated in these rims of hydrothermal systems that are associated with the impact craters? Could that be enough for organic chemistry and maybe life to happen? Okay. So we don't know the answer to that, but that's a very good question, and people we're interested in that.
Okay, thank you.
Okay, Neha is asking, since the Martian gravity is almost 1/3 of Earth's gravity, so which will not only degrade the health of astronauts but also give them space sickness. If we consider Mars as our new home, how will we cope up with this issue?
Oh, yeah, I love these questions about astronauts and people, but I don't know the answer to these. I do have friends at NASA who are medical doctors, and I know actually a few astronauts who study the physiology of the astronauts that go to the International Space Station, so for only a few months or maybe just over a year, and how their bone density goes down, and how their eyeballs bulge out, and their vision sometimes is impaired. So we're still trying to understand the long-term effects of lower gravity. And I mean, these are really good questions. We don't know. What we see from the astronauts coming back from the ISS is that they recover most of that bone density, not all of it. They recover most of their vision, but not all of it. So you see a lot of the astronauts, well, they're probably too proud, but they do need glasses often when they come back. Or in some cases, they've lost vision because of the low gravity. But we're still, this is a concern, right? Or rather, if someone goes to Mars and is living in low gravity, will that person be able to come back to Earth in the higher gravity? These are all questions that are, people are studying now, but also sort of in the realm of topics of science fiction too.
Okay, so yeah, young Bhumika is asking if our mission is on Mars, and if we went to another planet, so will it be successful or not? So I guess she is asking that if we manage to land on Mars, and if we plan for another planetary mission from there, so what will be the chances of the success for that?
So in other words, go from Mars to another planet? Is that the question?
Yeah, it seems that.
Yeah, I think most of us have not really thought about that yet. What we're thinking about is the moon, right? Moon's closer to Earth. It's only a few days away from Earth. Sorry, my light keeps going out. It's only a few days from Earth. And so would that be a staging point? Because it's a lot less expensive to leave the moon orbit than it is to leave the Earth's orbit. And by expensive, I mean how much fuel it costs, right? How much fuel it takes to leave orbit. So I think the question might be better addressed for lunar projects, and there is talk about, would we have a lunar base, and from there we would have a staging ground to go to Mars. In fact, that's sort of one of the ideas that the NASA administrators talked about, is first to Moon and then to Mars. So Moon is a good training ground, good practice, but we can come back from the Moon. It's a short trip. Mars is 6 to 10 months. So, but anyway, if you're a younger question poser, these are all things that you might have answers for in your lifetime. It'll be exciting. I'm looking forward to space tourism, personally.
So Arya is asking, is it possible that there will be life under the surface on Mars? Or
yes,
any signature
yes,
of life?
I love that question. Is it possible to find life under the surface of Mars? Well, yes. In fact, I was at a workshop in November, and the conveners published a paper from the workshop this year talking about what the general consensus from the community is about the 4 most likely places to find life on Mars that exist today. So extant life. And on the surface, it was in ice, right? Or rather in ice or in salt. And so there are four candidate sites, and the other 2 were deep in the subsurface. So maybe these water lakes, so several kilometers down, or, and this is my favorite one, in a lava cave. So because you're protected from the solar radiation, you're protected from the extreme shifts in temperature. The caves are going to be cold, but they're pretty much uniform temperature. And could some kind of microbial life still be there? And could it have deposited, or could it be depositing some kind of biomineral or a biosignature? And that's actually this sort of thing I'm studying right now up in the cave system in Northern California. So thank you for that question. But we don't know the answer yet.
Any questions do we have from our YouTube channel?
So we'll finish off this, and then we'll hop on to YouTube questions as well. So Tushar is asking, what were the challenges faced by NASA while making Ingenuity drone?
Oh, I didn't, because I just really didn't.
The atmosphere is very thin.
I just didn't really answer that question. There are many challenges, but the biggest one is, how do you get lift? How do you get lift from the helicopter when there's almost no atmosphere? Right? How do you get something? So you have these parallel blades, right? So essentially, and they're rotating, I can't remember, 24,000 RPM, rotations per minute. Is that right? So it's essentially, you have to, oh, Chinta, do you know the number? But anyway, you can look up the exact number. But anyway, they're rotating incredibly quickly. I mentioned they're a meter in length, so they're very large to take advantage of any sort of loft from the very low atmosphere on Mars. And then they have to be very light. So those are the biggest challenges, is how making the rotor blades light and rotating very fast to be able to lift in this environment. So JPL actually has a vacuum chamber that they can flood with very low amounts of gas to practice that. And so those were some of the challenges they thought were the most extreme.
Okay,
so the rover will have a very light camera on it. Yeah, go ahead. Sorry to interrupt.
Next question is by Dr. Ella. What are the effects of electric or magnetic fields on Mars as compared to, say, the Earth?
What are the magnetic fields on Mars? As I understand it, Mars has something they call a remnant magnetic field. So it's very spotty and sparse, and it's lower strength than on Earth. So when I read about this some years ago and heard some talks about this, I thought, well, if I were going to send humans to Mars, I'd want to go under that umbrella of the remnant magnetic field, thinking about protection from radiation. But I think it's not enough, right? There's no magnetic field sort of aura or lines to help deflect a solar wind. So in terms of absolute numbers, I don't know them off the top of my head, but it's very weak. So we think, that indicates that Mars once had maybe a dynamo in its center, right? A sort of a metallic core that has a dynamic and essentially is circulating. But because Mars is so much smaller than Earth, and further, Mars probably is, if it did have a dynamo, it's probably has solidified or mostly solidified, and as the planet cooled much faster than Earth.
Okay, so Hari is asking, does Mars have a weather system?
Does Mars? Yes, yes. Mars has weather. In fact, we lost a rover. I mean, we lost opportunity from a huge storm that encompassed, gosh, the bulk of the planet. And this has happened a few times in the past 10 or 20 years, where we've seen this, where just Mars becomes one giant dust cloud. And so, unfortunately, the exploration rovers, because they were powered by solar energy, they need that in the sunlight to charge their batteries. And so if there's a lot of dust, the dust covers the solar panels, and then they can't operate. So what had happened prior to this big storm where we lost opportunity, the second rover, we would get in seasonal storms that would come in and cover the panels, and then in the winter, the rover kind of shut down and just keep all of his energy just to keep it at enough temperature so it wouldn't collapse, right? But it wasn't very active. And then when the winds would come back and clear a large portion of the dust off, then the batteries could start functioning again, the solar batteries, and then the rover could get active again. So there are storms, and there are people who actually study global circulation on Mars, just like we do on weather patterns on Earth. There are a lot fewer constraints, because we don't know a lot about the details of the whole surface of Mars. And we see these dust devils. We filmed them. We see the changes in the size and the mass of the polar caps. So in the summer on Mars, the water ice and the CO2 ice primarily sublimates, and we think flows into other parts of the Mars, the globe rather. And then when Mars is colder in the winter months, then that ice reprecipitates at the poles. So also Mars having such an eccentric orbit makes its seasons more extreme as well.
Okay, next question is by Dr. Apparao. What is the effect of interplanetary magnetic field on Mars?
Interplanetary magnetic field. I'm not sure what interplanetary magnetic field is. Tinta, do you know, or Vendra, do you know what that is? And actually,
I think I can add some.
Space Geeks might be able to answer this better than I could.
Yeah,
yeah, interesting.
So this is actually something related to what I and Ankush have worked on during our PhD work. So basically on the Earth, and in fact related to this, we also had a space weather course just a couple of weeks ago at Space
I saw
Geeks.
that. Yeah, that looked really good.
Yeah. So this basically the Earth's magnetic field, it protects you, or to a very large extent, from the high energy charged particles and the high energy radiation that is coming from the sun in the case of coronal mass ejections and the solar flares. And whenever there is a coronal mass ejection, or whenever there is a solar wind, so in the case of sun, the magnetic field is embedded within that plasma. And so in the Earth's case, the magnetic field is there to protect you, but some of the particles do enter from closer to the auroral and polar regions, and that's when you see what is known as aurora, or the northern lights. And that's an indication of something known as a space weather that happens. And during that time you have certain difficulties faced by power grid systems and communication systems in high latitudes, and some of the flights have to be redirected away from the polar regions at that time. Now on Mars, there is no global magnetic field. So as Jen had just mentioned, that there is a very small remnant magnetic field at the southern pole. So without the magnetic field, the Martian atmosphere and the weak gravity is also to an extent responsible, that the Martian atmosphere is really exposed to this solar wind that's coming on from the sun. So what happens when the solar wind interacts with the Martian atmosphere? The interaction causes the particles in the atmosphere to get charged up, and then the solar wind and the plasma just blows away these charged particles. So this is the way how the Mars is actually losing its atmosphere slowly over a period of time.
So that's thanks for that explanation, Vindra. That's really interesting, because the MAVEN mission, and I think actually the MOM mission, the India mission on Mars, are studying the rates of loss of the Martian atmosphere, right? How fast this is happening. And so I always think of the fact that Mars has smaller than Earth, so has lower gravity, and that's why the atmosphere is higher, or the atmospheric depth is greater than on Earth, because the gravity just can't suck it down as much, right? But also it affects the rate, since it's more expanded, it affects the rate of loss of the atmosphere. But also, as you mentioned, if there is higher flux of solar wind, that would enhance the amount of ionization. And if there's no magnetosphere to protect it, that would increase it as well. So not only the lower gravity, but also the lack of protection. This question, which I think is really interesting, it makes me think of something I read or saw also some models of in the news this year about how the Earth's magnetosphere is actually blown by the solar wind, right? So that actually the moon is largely in the shadow. I think, Chinta, we had talked about this, the moon is largely protected from the Earth's magnetosphere. But with the wiggliness of the magnetosphere, there are actually times when the moon is not protected, and then it's very exposed to that solar radiation, and that could be very hazardous for astronauts going forward. So once again, go to a cave. There are lots of caves on the moon. Anyway, oops, shameless plug.
Okay, so there are so many more questions.
Project.
Someone else. Oh, go ahead. What?
Dr. Jane Blank, can you please talk about your Braille project and the robotic missions, what you're studying, which are of aspects from Mars?
Thanks, Chinta. I'd love to come and talk with you on another time about the mission. So this is a mission to Northern California, where they're to a site called Lava Beds National Monument, where there are more than 850 known lava caves. So more than 50 kilometers of tubes. And I've been working there for 3 years with a group of scientists. And when we look in these caves, we find what we call cave corals, right? But they're actually silica biomineral deposits that look like, and they're smaller than a centimeter, and often a lot smaller. But they actually. Oh, here's an example of something. And you see these little things, they're little bubbles. These are all biomineral precipitants. So this is evidence of life. And so I'm working with a team of scientists to characterize these things for the chemistry, the microbial communities that make these things, the lipid geochemistry, lipid organic geochemistry, and all these signs, thinking that this might be something that could be preserved over geologic times. And if there was life on Mars in a cave, there are lots of, this is sort of a house of cards, but if there was life and it persisted in a cave, we could find these because they've been preserved in the record, in the rock record, and they would have been protected from the surface, erosion, etc., because they'd be underground, but not buried. So I'm working with a science team to characterize these things. And another cool thing about them is because they're in volcanic environments, they're mostly silica. So first I thought they'd be carbonate, but they're actually not. They look like corals, but they're mostly silica. So it's really interesting. And so more like diatoms and things like that. I'm talking faster because I'm excited. but what we're also doing is I'm working with the robotics team, first at NASA Ames, where I am. And actually my team was pulled off to work on the lunar Viper mission. So I was very sad about that, but I don't blame them for being reassigned, and the moon trumps Earth in terms of a mission. But then I've now started working the beginning of this year with a group from the Jet Propulsion Lab, and it's actually bigger and more exciting. They have more exciting capabilities because we're using these Boston Dynamics spot robots and the legged dogs to walk in the caves, and we're developing mission concepts. I mean, I'm the token scientist, so it's really they're developing these things first to compete in a subterranean challenge that's a U.S. Department of Defense technology challenge. But we're using all of the technologies and the software and autonomous mapping and autonomous target selection that they've been developing for this potential military thing. Now we're applying that to our cave mission. And so I'm so excited about this. And of course, we started doing this and then we had the pandemic. Or we had the pandemic. So we went on our first mission with the Boston robots last month. We're going in 2 weeks again, and then we're going in November again. So in each time we're doing more tests and trying to demonstrate how these rovers, but these robots can walk into the caves. With the other robot, was a wheeled robot, we had to carry it in, and it was so heavy we had to take it apart and then carry it in and then put it back together. So it's very exciting, and we're trying to mimic some mission scenario activities in these caves on Earth to help us get ready. And as I mentioned at the very beginning, it takes a long time to get a mission to another planet. So we don't have, NASA has not said we're going to Mars, Martian cave yet, but we're trying to do all of the groundwork to show that why not, right? Why not? So, and if NASA doesn't want to do it, I know that somebody will want to do it. So it takes a long time to get ready. And if any of you are interested in this sort of thing, contact me, because I think it's super fascinating project. And also JPL is always looking for people who are interested in robotics and software development. We're doing a lot of machine learning. Because we have we have thousands and thousands of pictures of our features in the caves and mapping technologies, and it's a really exciting project to be part of, I think. And I'm the leader. So anyway, I'm not the principal on a mission to Mars, but I'm going to Northern California. So, okay, thanks, Chinda.
Must be tired, right?
We can take perhaps last question.
Yeah.
Is that okay?
Yeah.
Jen?
Yeah, that's sure.
Yeah. Okay, so the question is basically a comment on the idea of life that we have based on the Goldilocks zone and presence of liquid water on the Earth. So the question is there a possibility that life in any other form can thrive without the presence of liquid water on, say, other planets?
Well, okay, that's a very interesting question. And if I understand it, it's a question of could life survive outside of the Goldilocks zone? Now, in terms of whether life could be another form like silica, like we see in Star Trek, I'm not going to address that because my thinking is guided with the scientific method, which is based on empirical method of what I know or observations. But in terms of the Goldilocks zone, that's a really good point, because we initially thought you had to have liquid water on the surface of a planet. But what we've been finding more and more since that first discovery with Europa some years ago, that Europa has a subsurface ocean. And it seems that many of the moons in the icy part of our solar system have these subsurface oceans. I think there are probably at least 10 other ones that we know of, including Enceladus, including Titan even, below all the hydrocarbons. So there may be a liquid water ocean, Ganymede. Even Pluto may have a liquid ocean underneath, or something briny. So if that's the case, and we do see life, we know there is chemosynthetic life, right? Life that doesn't need light but lives on the chemistry, or autotrophic life that takes energy and raw materials from rocks and water to make more life and get the energy to survive from that source or those sources. So why not? I think that means that our thoughts are the constraint of the Goldilocks zone really is a constraint no longer, right? Because we can look for life in any place where we could find liquid water, and that could be in the subsurface. Of course, the biggest challenge is how will we access that liquid water, right? One of the reasons people are so excited about Enceladus, even though it's 9 years away by probe, is that the Cassini mission, so Enceladus is one of the moons of Saturn, and the Cassini mission that was orbiting Saturn for 9 years or 12 years, I can't remember, made many flybys of this small moon and saw plumes of aqueous briny material jetting into the atmosphere of the small planet, or small moon rather, and were able to see that there were hydrocarbons in that plume. So that's why people are very excited to go back to Enceladus and see if, hey, this is communication from that subsurface ocean to the surface. What else could we find there? So, and likewise with Europa. So anyway, I hope that answers your question a little bit.
Yeah, so I think that before concluding this session, I want to uh, thank few people. Because of them, this whole event was possible. First of all, Dr. I thank Dr. Jan Blink and for giving this talk. And we are very fortunate to have you. And I think we are really excited to know more about Mars, and we are really inspired by your talk. And I'm
Oh,
sure participants as well. And
may I
definitely,
just say, sorry, Chinta, to interrupt you, but I want to say that I can't believe that so many people have stayed on the line for so long. I've just looked at the participants, and thank you all for celebrating World Space Week with me and with the Space Geeks. But also, Space Geeks, I am so inspired by you guys. I mean, I just love the
Thank you.
fact that essentially you're sort of crowdsourcing or crowd, this is a complete volunteer effort on your part, and you're also knowledgeable and interested and interesting. And I really look forward next time I can see you and maybe more Space Geeks in person in Mumbai.
definitely,
Sure,
definitely.
sure.
And then let me come to Amity University. Of course, Dr. Vaibhav is here with us representing Amity University. But I also want to thank Dr. Siddharth Pandey, who is heading the Astrobiology Center at Amity University. Somehow, because of his Ladakh mission, he is not present here. But his wishes are with us. He told me over phone that just go ahead with the event. And so I really thank him that he really took our our proposal, and so that we could co-organize this event with Amity University and Amity Center for Astrobiology. And in fact, Dr. Jane Blank, she herself is associated with Amity University, and she takes astrobiology course over there. And Vaibhav, do you want to add in something?
Uh, Yeah, so thank you, Dr. Jain. No, I just had to ask a final comments from Dr. Jain on there was a recent, uh, eyes on Venus with the phosphine being discovered and how we can connect to the Mars. Because I'm not sure somebody has asked, but maybe with the final comment she can actually say something about it. And how it excited and how is the new generation scope, like again, of course there is a lot of mission we can think about and we can include further studies about it. Yeah.
Well, in terms of the discovery of phosphine, which is an organic compound that has phosphorus and oxygen, and it's one that we can generate in some chemical plants, but otherwise we don't really see an abiotic source of phosphine on Earth. So when it was detected and verified as a spectral line in observation of Venus, some people were very excited. Could there be life in the clouds of Venus? Well, I think it's a very interesting detection, and it certainly has inspired a lot of discussion and thought. But it's just that and I know that actually NASA has is pushing for a mission concept and mission to Venus again. But I think this is in large part due to an Indian American national from Sanjay Gupta from the University of Wisconsin in Madison. And he has spent the last 20 years traveling around the world pushing Venus. And I've had the pleasure of meeting him a few times, and he's so inspirational because you have to go to Venus. You talk with him, you have to go to Venus. I mean, you have to go. But in terms of phosphine as a indicator of life, I'm skeptical. I mean, I'm all for going to Venus, but we see phosphine in the spectral lines if we look at Jupiter. So it's not a unique detection. It's just we hadn't seen it before. I don't want to poo-poo anything, but it's not an indication of life as far as I know. It's just an indication that we should look deeper.
Yeah. And
Thank you so much. I mean, yeah.
Yeah, I also want to thank students from NIT Trichy, because we have also Professor Raghavan from NIT Trichy, who actually requested students to join for this talk. And we also have speakers who gave first two talks with us present among participants. So I think they also must have really liked your talk. So I also thank Professor V.K. Jain and Professor V. Mahadevan from ISRO. They also are among the participants for your talk. And they had in fact given first 2 talks with us. So I also thank them that they are present in the audience. And I also thank like all the speakers who made this event very successful. And thank you for your support and encouragement. And I think we also have Swapnil Gaul, who also has its own antenna software with whom we actually co-organize the 2 talks. So I also thank Swapnil. And it's really good to have you all on weekends, spending your weekend and coming to enjoy these talks. And I think we have really, I feel from my side that we have really contributed to create awareness about space. And I'm sure among all these participants, especially younger participants, they really take up uh, the opportunities and take up subjects related to space and space technology. So I think with that, let me conclude this session, and thank you to Space Geeks team who has been of tremendous support, especially Vaibhav, Virendra, Ankush. Even Ankush is joining, but he's at right now Trivandrum. He has just joined SPL at ISRO, but and there is a lot of network fluctuation, and somehow we were trying to coordinate these events and all the talks, so that we ensure good participation. So I really thank everyone. I really thank media, because we also had a pre-event article in regional newspaper version of Times of India. So I really thank them, because when we are celebrating World Space Week, there is a role of media also to bridge the gap, to connect society and space experts together to create awareness. So I really thank media. And I think with that, we can conclude this session. Again, thank you so much, Dr. Jane Blank, and we really look forward to have more such talks from you.
It's a pleasure. Nice to see you. Thank you all for your time and for attending. And thanks to the Space Geeks again.
And thank you, Blue Marble Space Institute of Science. I forgot to mention that. Yeah. So, yeah, because
All
we're
right.
also co-organizing this.
Have a great rest of your weekend, everybody. And I hope to see you again, maybe in person.
Thank you.
All right. Bye.
Have a great weekend yourself.
Yeah, thank
Bye.
you. Bye. See you later.
Bye very much.
Good night, everyone.
Good night.
Night. Good night.
Bye.
Bye.
Bye to everyone. Good night.
Good night.
Bye, everyone.
Good night.
God bless you.
Thank you. Same to you.
Dr. Jane,
Just
it was
a
wonderful.
moment. Can you take a small group picture? If
Oh, yeah,
people can-
yeah. Some people are still there. We can take a group picture, group selfie. I request everyone to turn on their cameras if they can.
Hey.
Yeah, Virendra, are you taking?
Yeah, I'll take it.
Okay. So just one
Everyone,
minute.
please, can you turn on your cameras, your videos?
Yes.
I will just take a group picture quickly. Okay.
We'll post this on
still
the Facebook page, so keep looking
Yeah.
for the
Oh,
picture.
cool.
Yes. And Virendra, just take another section picture also, because there are other participants.
Yeah, there are 2 sections, yes.
Yes, so you just keep taking. So, yeah. So it will be great if participants can turn on the cameras, so we can take a quick picture.
I love seeing everybody.
Yes. Okay.
Good night, Dr.
We are
Jane.
done.
Good night. Good night.
Good night. Okay, Virendra done?
Yeah, I'm done.
Okay. Thank you so much, Dr. Jain, and goodbye, good night, and happy weekend.
Okay, good. And hey, you guys are awesome. I mean, seriously, I'm inspired by you. So I look forward to our next interaction.
Absolutely.
Okay.
Like, yes,
Thank you so much.
absolutely. Thank you so much.
All right, take care. I'm going to sign off.
Okay, bye.
Bye bye.
Okay, bye-bye.
Bye.
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 Okay, Vaibhav, can you please end the stream on YouTube?